Hey guys, okay, so today we're going to talk about states of matter. Okay, now for the most part, states of matter should be common or prior knowledge, but we're just going to go over it, review it, make sure we understand how we can define it. Okay, oftentimes we know the states of matter. Okay, and our states of matter are solid, liquid, gas, and plasma. But sometimes if I were to like ask you to define solid, what a solid is, you could give me examples, but actually putting the definition to words is sometimes more challenging than you would expect, okay? Plasma is often our new one, so that if we haven't heard of one, that will probably be it. So let's talk about solids. Okay, so solids have particles that are closely packed together, and you can see that in the image down here, or we're looking at the actual particles. Okay, we have specific geometric arrangement, a definite volume, so think about it like you can measure the volume of a solid, a definite shape, so it does not take the shape of its container, and the last little bullet here is really important because oftentimes when we look at a desk or a chair or a table, we say that that it's not moving. Well, okay, yes, it's not. Well, that depends on the point in which you're looking at it. But yes, technically it's not moving. Okay, but the particle level, it's really, really important to understand that solids, the particles do move. Now they don't move far, and they don't move far because as they're moving, they hit one another. Okay, so it moves and then it hits one, and so then it moves back. So it can't move very far. So the particles in a solid are going to vibrate. Okay, in a liquid, so if you look here at the particles, the liquids are starting to get a little more spread out, okay? So the liquid is going to move a little bit more. They're actually going to flow. These particles are going to transfer energy as they hit one, and then it continues to move. Again, they have the ability to flow. We do have a definite volume, so remember we can measure the volume of a liquid with a graduated cylinder, and then it does not have a definite shape, and you and I know that because if you were to spill your cup of water, it takes the shape of the table or the floor or wherever you spilled it. All right, gases. So again, solids barely vibrate, liquids move a little bit more, and gases are going to move the most rapidly and the most spread out, okay? So these are going to be moving far apart from each other. These do not have a definite volume, okay? Meaning I can't hand you this amount of air and ask you to get the volume of it. Now, don't get me wrong. If I had a sealed container and you pumped their air in it, then we could contain that amount of volume. Okay, but that's really more of what that would be, is containing that amount of volume, okay? And then obviously no definite shape because it's not even gonna take the shape of its container. Well, it will if it's an enclosed container, but if it's an open container, it's gonna dissipate out into the air, okay? And then gases are able to flow. And again, these are gonna move more rapidly. Now, the one that you may not be familiar with is plasma. And when I say plasma, we're not talking plasma like in blood, okay? This is very similar to a gas. Okay, so it's rapidly moving, spread out, no definite shape, no definite volume. But the difference here is it has positive and negative particles. And remember, opposites do what? Opposites attract, okay? And it's that positive and that negative that are gonna attract, and they're actually gonna have high energy collisions. And that's what produces this state of matter, okay? This is the most common state of matter in the universe. Now, not on Earth, I did not say that. Okay, in the universe. So let's talk about why. So let's figure out where we see plasma. Okay, fluorescent lights, when they are on, they are in the state of plasma. Think about it, guys. When the light switch is off, okay, that opposite charge does not exist. When the light switch on, the electricity creates this opposite charge, causing the collisions. Neon lights are another one. Lightning, stars, and so if it's in the stars, then that means the sun, right? And that's where we get this most common state in the universe, okay? Also auroras, so aurora borealis, so that would be like your northern lights, right? So here's a picture of the northern lights. And again, we want to make sure that we understand that we have this positive and this negative, but unlike this image, because obviously it's an image, it can't move, they're not sitting still, they're moving rapidly, and because they're opposites, they're gonna pull together and create these collisions. All right, so real quick, the kinetic theory. This is the kinetic theory is a theory that tells us about particle movement and particle behavior. Okay, so first it says that all matter is made of particles. Okay, particles are in constant motion. All particles are in constant motion. Okay, the particles that collide, they're going to collide with each other, and they're going to collide with the sides of their container. Okay, all right, so let's watch this short little video. Maybe. Maybe. And second.
The kinetic theory explains the properties of the different states of matter. All the particles in a solid, liquid, and gas are the same. The only thing that changes is the amount of energy they have. Solids have a low amount of energy, too low to overcome the strong bonds that hold the particles together in a regular pattern, but not too low to stop movement altogether, as they still vibrate about a fixed position. Solids are also incompressible, because there is no free space between the particles for them to move into. If we give a solid some more energy, it will eventually loosen the bonds between the particles and allow them to move over each other, which will result in taking the shape of its container, which is what we call a liquid. Similarly, liquids cannot be compressed because there are no free spaces between the particles, which is why if you were to jump off a really high diving board, the particles in the water would for a split second represent the properties of concrete because the particles haven't had time to move out of the way for the unfortunate diver. Gases have a lot more energy and move about the container very quickly. And unlike solids and liquids, they can be compressed because there is lots of space for the particles to move into, which is how a paintball gun works. By compressing the air very closely inside a tank and releasing it in a short burst to propel the projectile onto someone's backside. Ouch. Okay, so again, just a quick overview of the kinetic theory. Now let's talk about some different properties of a liquid. Okay, so viscosity is one of them. When I tell students, when we think of viscosity, I always think of syrup, okay? Sometimes, if you've ever gone to Cracker Barrel, they heat up their syrup. Well, what happens when you heat up syrup? It starts to move more swiftly. It moves a lot more quickly, or flows very swiftly. That's changing the viscosity. Okay, so viscosity is resistance to flow. Now, it's determined by the molecular structure, which is why molasses, you ever heard the saying, slow as molasses, flows really slowly. But viscosity can change with temperature. So if you heat up a substance like syrup, it's going to lower the viscosity. It lowers the resistance to flow, which is why the syrup flows more quickly. If you cool down the syrup, so let's say if we were to put it in the refrigerator, okay, it's going to increase the viscosity or increase the resistance, which is going to cause it to flow way slower. Okay, so viscosity, the resistance to flow. Buoyancy is the ability of a fluid to exert an upward force, okay? It determines if an object's gonna sink or float. Object will float if its density is less than the fluid that it's placed in. And lastly, now I added this because a lot of times I'll have students that'll say, okay, well, we get solid, liquid, gas, plasma, but what about like shaving cream or like whip? It's where does it fit? Or Jell-O, right? Where does it fit in this category? Okay, and that's more of actually a mixture, okay? Well, we're gonna talk about mixtures one day. But specifically, they're considered colloids. Now, they're considered colloids because they're made of tiny particles of solids or drops of liquids or bubbles of gas that are evenly distributed. So they're not dissolved, they don't sink to the bottom, they don't float to the top. They're evenly distributed, okay? And they're thoroughly mixed. So examples of this would be like Jell-O, shaving cream, whipped cream, hair gel, mayo, and even milk are all colloids. All right, so let's talk about phase changes, okay? So now we're gonna go from one state of matter to the next. So when we talk about changing states of matter, we're gonna be focusing on energy, okay, and what that energy does. So right now we're gonna talk about adding energy. Now, please understand, we're gonna be adding energy in the form of heat. Now, when we add that energy in the form of heat, it's gonna cause the temperature to increase. But remember, we're not adding temperature, okay? We're adding energy in the form of heat. Okay, so if we have a solid, we're gonna melt into a liquid, which we should be okay with. A liquid, we're gonna evaporate. Now this could be vaporize or even boil, and we're gonna talk in a second about the difference, into a gas,
Okay, and now here's probably a new one, and this is going directly from a solid to a gas. So for this one, we're not even hitting that liquid state. Okay, so we're gonna sublimate going directly from a solid to a gas. So this would be like dry ice. Have you ever seen dry ice? And we're gonna watch a video in a second that will show you some examples, for example. Okay, so please understand, as we're adding energy, we start with a solid, and so our particles are barely moving. We add energy, they're gonna start getting a little further apart and moving a little bit more into a liquid. As we continue to add energy, it's gonna move even further apart and even more rapidly into a gas. So we see that natural progression of that kinetic energy, okay? All right, so evaporation. So evaporation is what happens in the swimming pool, right? Have you ever seen, if you have a pool or go to a pool, a lot of times you have to add water to a swimming pool. Well, guess what? The pool didn't have a leak, the water evaporated, okay? And we talk a lot about evaporation with the water cycle, okay? This only occurs at the surface of the liquid and it's below boiling point, okay? Now, vaporization is a little different. Vaporization is boiling, okay? So vaporization occurs throughout the liquid and it's at the boiling point, okay? So it's gonna be really, really important, guys, and if you aren't writing anything down, I highly recommend you, I don't know, start writing stuff down. It's gonna be really, really important that you know the difference between evaporation and vaporization. Now, if I were to give you like a phase change, and I didn't give you specifics on what caused it to go from a liquid to a gas, then that might be a little different, okay? All right, so that was adding energy, okay? Now, again, we can't add cold, okay? Cold's not really a thing. We'll watch a video on that probably tomorrow, but we're gonna remove energy. We're removing energy in the form of heat, okay? So that is gonna in turn lower the temperature, okay? So we start with a gas, we're gonna condensate to a liquid, right? So gas to liquid is condensation. So this is like the sweat on your water glass or the dew outside in the mornings, right? Or the clouds, condensation. From a liquid to a solid, that's freezing. This can also be called crystallization, okay? Because we're turning to a solid, okay? And then, okay, so opposite of sublimate would be deposition, okay? Deposition is going from a gas directly to a solid. And we'll see that in a video in a second to help that make a little more sense. So again, guys, understand that now we're starting at a gas and we're all out, spread out, moving really fast. We're removing energy. So we're starting to slow down, getting a little closer, turn into a liquid. We remove even more energy. They're moving even less, and they're really close together to a solid. So we should be able to see that natural progression. All right, here's this video.
This is elemental iodine. It's a dark, black, bluish solid at room temperature. Iodine is the heaviest of the stable halogens. When we heat up the iodine, it's going to turn directly from a solid into a gas. The iodine vapor has a beautiful purplish color. This process is called sublimation, turning directly from a solid to a gas. And we place a cold flask over top of the vapor. The warm vapor will cool off on the cold glass, and the gas will turn directly into a solid. This process is called deposition. In this case, we're seeing the deposition of iodine onto the cold glass surface, where we would say that iodine is deposited onto the cold glass. We can't do this experiment in our science classroom because the iodine gas can be harmful to us.
All right, guys, so let's talk about a phase change graph, okay? So if I were to draw a phase change graph, okay, it's gonna look, and here's my graph, like this, okay? So let's talk about this. So the bottom is always gonna be energy, okay? And now this is the increase of energy. Now we've already said we're increasing energy in the form of heat. And that increase of energy is going to cause an increase of, I can't write sideways, sorry, temperature. Okay? So, no matter your substance, the basic phase change graph is going to have the same shape. Okay? Now, your plateaus, your slopes, they may vary, but the shape is basically going to be the same. So, we're going to start at our lowest energy. At the lowest energy, we know we're at a solid. Okay? And then as we increase energy, we move to a liquid. Make sure you can see this on the screen. And then as we continue to increase energy, we go to a gas. On the web quest yesterday, it continued out to a to plasma, but we're going to stop here for the majority of ours. Okay? So let's talk about this. As we add energy, we're going from a solid to a liquid. Okay? Now remember, when we move from a solid to a liquid, that's considered melting. Okay? Now please understand, this line plateaus. Okay, my line might not be super straight, but it should be completely flat. Okay, we are still adding energy to the substance, but at this plateau, that is where we are undergoing the actual phase change, okay? And even though we're still pumping energy into the substance, it's gonna take a good bit of energy to actually change the state of matter, which is why that energy does not cause the temperature change at this point, okay? So as we're undergoing the phase change, all of that energy is necessary, is needed to actually change the state of matter. So therefore, you don't have that temperature increase. Again, just at the plateaus. Okay? So again, we're in a solid, we melt to a liquid, and we, let's see, evaporate, vaporize, boil, okay, depending on what your situation is. We vaporize to a gas. Now, there's another one, and we mentioned this one, going directly from a solid to a gas. Remember, we saw it with the iodine, okay, and this is sublimation. So we're going to sublimate directly from a solid to a gas. Okay, now that's adding energy, right? And again, energy in the form of heat. Now, what about if we were to remove energy? Okay, if we were to remove energy from a gas, we're going to condense. Or condensate, I guess kind of condensation. So we're going to undergo condensation to a liquid. And then from a liquid to a solid, it's going to be freezing. Now from a liquid to a solid can sometimes be called crystallization. So you'll see it in both terms. Okay, so condensation, freezing. Now, we also have this little guy that goes directly from a gas to a solid, and that's called deposition. I'm going to change colors because it's a little darker. I don't know if you can see that. Let's go back to this. Okay. Now, so we're going to read these graphs. Okay, I expect you to be able to read these graphs or to be able to label these graphs. Okay. So if we looked here, here's a good practice problem. All right, now let's just make a quick note. This is a sample graph, okay? This is not water, and we can tell it's not water because of the boiling points and freezing points, and we'll get to that in a second. So again, different substances are gonna have different slopes and different plateaus and different space spots, like temperature-wise. But we know the basic shape's the same. So this is where I'm a solid, a liquid, and a gas. Do you see it? Because it's sloped flat, sloped flat. Okay, so the first substance, or the first question, excuse me, asks, what is the freezing point? Now I need you to understand, it's asking you the freezing point. Freezing point, boiling point, melting point, these are all temperatures, okay? So if we were to look at the substance, okay, freezing is going from a liquid to a solid, so my freezing point is gonna be right here. The temperature at which it freezes. Now that temperature is gonna be 5 degrees Celsius. Okay, the next question asks my boiling point. So what would my boiling point be? Where am I boiling? Okay, so going from a liquid to a gas would be boiling. So it would be right here, D. But again, remember, it's not asking you for the letter, it's asking you for the temperature. Okay, so that's going to be 15 degrees Celsius. All right, the next one asks you for the melting point. Okay, so the melting point is when we're going from a solid to a liquid. Okay, so what would your melting point be? Okay, your melting point would be 5 degrees Celsius. Okay, and it's 5 degrees because if we're going from a solid to a liquid, it's going to be right here. And it's going to be 5 degrees. Now, a little side note. I know the melting point and the freezing point are the same. It's supposed to be. The boiling point and the point of condensation is the same. Remember, the difference is whether we're adding energy or removing energy. Okay? So, the next question says, what letter represents the range at which a solid is being warmed? So it's going to be the range at which we have a solid and it's being warmed. So the only point at which we have just a solid, that's going to be A. Now the next question asks, what letter represents the range where a liquid is being warmed? So at what point are we at a liquid? Now just a little side note, remember, B is we're going to be solid / liquid. So we're going to have a little bit of solid, a little bit of liquid because we're transitioning. Okay, same thing for D. So the point at which we have a liquid being warmed is going to be C. Did you get it? Right here is where we're in liquid. All right. So the next question says, same graph, what letter represents the range of gases being warmed? So where is a gas being warmed? So again, yes. So again, if we're going to label this solid, liquid, gas, so our gas is going to be E. Okay. Now, the next question says, what letter represents the melting of a solid? So where, not where we're a solid, but where are we melting? Okay, so the melting of this solid. B. Okay, the next letter says what, the next question says, what letter represents the vaporization of a liquid? So remember, vaporization is when we're going from a liquid to a solid. So what represents that point? Which is going to be D. What letter represents condensation? Guys, again, I know that's the same letter as vaporization, and that seems kind of strange. But guys, think about it. The boiling point of water is 0, it's 100 degrees Celsius. Well, at what point would it begin condensing is also 100 degrees Celsius. What temperature do we melt? 0 degrees Celsius. What temperature do we freeze? 0 degrees Celsius, okay? The last question says, what letter represents crystallization? Again, crystallization is just another term for but turning into a solid, okay, or freezing. So that would be B, okay? So here's another way to look at it. You're gonna more likely see the sloped phase change graph, but this just helps us to kind of put all of our changes into one image. So we go from a solid, we melt to a liquid, vaporize to a gas. Ionize is creating positive and negative ions, so that would be what would kick us to that plasma. Or deionization, so taking away it, we turn it to a gas, we can undergo deposition to a solid or condense and then freeze. Okay, so again, just another way to kind of see it all organized. Now, super duper duper important, okay guys, as we go from a solid to a liquid to a gas, I can't stress enough that we are not changing the mass of the substance, we are not changing the substance itself. Whether it's ice, liquid water, or water vapor, it's still H2O. We're not changing the substance. So phase changes do not change the substance. All we are doing is adding or removing energy, okay? And you're gonna hear me say this a lot, because this is a really big misconception, okay? Water boils, it's still water. It just turns into a water vapor, okay? So please, please, please make sure that we catch that, okay? Awesome, guys. Thank you. Have a good day.